let's go over the answer here. Okay, well first off, let's make sure we understand this question. Alright, the question says, the car company says 28% of their cars are silver. Okay, so you go to this car company, if you pick one car, what's the probability that it's silver? 28%, okay? But we're not taking one car, we're taking 50 cars at random. We're randomly selecting 50 cars, and we're asking what's the probability that of these 50 cars, at least 36% or more are silver, okay? So we're expecting around 28% to be silver, but sure, we can get more than 28% silver. And so, what is the distribution of p hat? P hat comes from a normal distribution. Alright, and what's the mean of this normal distribution going to be? My mean is going to be p, which is 0.28, okay? Now it's very important that we put things as p and 0.28. If you use 28, it's not going to work, okay? 28% is 0.28. You got to get used to dealing with decimals even if things are presented to you as percentages. What's the standard deviation going to be? Square root of 0.28 times 1 minus 0.28 over 50. Alright? Just want to make sure this is okay with everyone. Again, if you have no idea where certain numbers are coming from, you got to say, hey, I don't know where that number is coming from. Okay, I take the square root of this, I get 0.0635. Okay, 0.063498, but that's close enough. I'm asking what's the probability that 36% or more than 36% is silver. So in my normal distribution, don't blurt it out, just think what number goes in the middle? 0.28. And then I'm drawing a cutoff at 0.36. So what is my z-score? Again, my cutoff is 0.36, not 36. If you put in 36, it's not gonna work, okay? So my z-score is 0.36 minus 0.28 divided by my standard deviation of 0.0635. So on top I have 0.08 divided by this, and I get 1.26. A z-score of 1.26. Okay? It's all good? And then now, I look this up in my z-table. And when I look up 1.26, I get 0.8962. But I'm asking for more than 36%. Okay, if I said 36% or less, the answer would be 0.8962. But I'm looking for this side. So I do 1 minus that. And this is my answer, 0.1038. There we go. Okay. Yes?
So, what if we just kept 0.063?
Okay, then you probably got like 1.27.
I got 0.1020. That's the final answer.
Okay, that's fine. I recommend keeping about 3 or 4 decimals, okay? If you do that on next week's quiz, I'll give you full credit, okay? On the final exam, when it's multiple choice, what might happen is you won't see your exact answer available in the answer choices, and you're going to have to pick the closest one. Alright, okay, so start this in your notes. If you can do this problem, if you did fine on this problem here, one of the problems on next week's quiz, you'll do just fine, no problem, okay? If you struggled with this problem today, alright, study it so you're ready for next week's quiz. Okay, and of course next week it's not going to be silver cars and 28%, it's going to be something else, but it's going to be very, very similar. I've been saying p hat, the sampling distribution of p hat, comes from a normal distribution. Okay? The idea that p hat will come from a normal distribution that's known as the central limit theorem. CLT. Okay, it's pretty cool. There's a warning though, in that a few conditions have to be met in order for this thing to work. Okay? In order for the central limit theorem to work, in order for us to use the normal distribution and be able to answer questions like this, which depend on the normal distribution, a few conditions must be met. Number one, the sample must be selected randomly. Randomly and individuals independently. Random and independent. This is known as the random and independent condition. Alright, and what that means is that in the description of the problem, it must say that the items in our sample were selected randomly. Okay? Just like I said, we selected 100 people from Los Angeles at random. Okay? If I didn't select them at random and I went to some neighborhood that was predominantly one ethnicity, then I wouldn't have the same properties where we're looking for 40% white. Okay? So, random and independent. We got to select randomly. So, on next week's quiz, I'm going to have a little section where I'm going to describe little problems, and I'm going to say, are the conditions for the central limit theorem met? And you got to say, okay, does this say that things were selected randomly? If it says if they were, then this condition is met. If it doesn't say it was selected randomly, then this condition is not met. Condition number 2, okay? The sample size cannot be too small. Sample size cannot be too small. Okay. So how do we know if the sample size is too small or not? Okay. Well, we have to look at n and p. Okay. So n times p has to be greater than or equal to 10, and n times 1 minus p has to be greater than or equal to 10. So whatever n is and whatever p is, check these two numbers. Both of these numbers have to be bigger than 10. If that's the case, our sample size is okay. If either of these numbers are less than 10, your sample size is too small. Okay? So this is the large sample condition. finally, the population that we're selecting from also has to be big enough, okay? The population from which we are selecting, or from which we select our sample, must be big enough in that the population has to be at least 10 times bigger than our sample. Okay, that's the big population condition. These are the three conditions. All three conditions must be met in order for us to use the central limit theorem. Okay, let me okay, so in this problem where we're talking about drawing cars from this car company, okay, is the first condition met? Were the cars selected randomly?
Yeah.
Yeah, it says if you randomly select 50 cars, okay? So there, that condition is met. What about condition 2? Is our large sample condition met? Okay, well how do we check that? Okay, so there's two numbers I gotta check, right? So, random condition is met. Okay, so large sample. I gotta do n times p, which in this case is what? 50 times 0.28. What does that equal to? It's like
14.
14.6? No, just
No,
14.
14.
14, okay, great. And then n times 1 minus p. Okay, so that's 50 times 0.72. That's equal to 36. This is bigger than 10, and this is bigger than 10. So my large sample condition is good.
That check means independent? Oh, okay, I understand.
Okay, large sample condition is met because n times p gives me 14, which is bigger than 10. N times 1 minus p is 36, also bigger than 10. Okay? Is the big population condition met? Okay? Now this is, it's not explicit in this problem. How big does our population have to be? It has to be 10 times bigger than our sample, so give me a number here. It's got to be at least 500, right? My sample is 50 cars, so the population has to be at least 500 cars. Okay? Is it reasonable to believe that a car company has made more than 500 cars?
Oh,
yeah. Okay, so that's reasonable. So the big population is met. Okay? Population reasonable to believe the car company has made over 500 cars. Yes?
Will it usually just be based on reason, or will it ever state how much the population?
Yeah, sometimes I will state it, right? Maybe I will say a school has 400 students enrolled. We've taken a sample of 50 students. Taken a random sample of 50 students, and p is some number, okay? P is 0.4. Are any conditions violated? You tell me the big population condition is violated because the school has 400 students, and my sample is 50. 400 is not 10 times bigger than 50. Yes?
So when you check to make sure the sample size, you have to check both of those?
You have to check both.
So if either one is under 10,
If
then
either
it's
one
too
is
small?
under 10, the sample size is too small. Okay?
So if any of these conditions are not met?
Any of these conditions are not met, you cannot use central limit theorem. Okay? So if you want to use central limit theorem, all three of these conditions have to be met. Okay? So maybe I'll try one more example. Okay, or here. I'll just leave that up. Okay. So let's just hear this out. Okay. I decide to conduct a survey. Okay. So I walk around campus and I interview 100 people. Okay. UCLA has over 30,000 students, and I believe P to be equal to 60%, being I don't know, the proportion that use a map. I have no idea. Okay. Are any conditions violated? So I said P is equal to 60%. I've taken a sample of 100 people. UCLA has over I don't know, what did I say, 20,000, 30,000 students, and I walked around and I surveyed people. Are any of the conditions violated?
Is that random?
Yeah, number one. Okay, that's not a random sample. Okay, walking around campus will not give me a random sample. So the very first condition is violated. We cannot use central limit theorem.
How
Okay.
is that not a random sample?
Because I'm walking around.
Select who
He
you
selects
interview, I guess.
Huh?
It's like because you select who
You're
you're
selecting.
interviewing walking around.
No, I mean, I'm only going to see people who are walking around on campus, okay? If I truly wanted a random sample, I got to get people who, you know, maybe only certain students show up on Tuesday, right? Okay, some students only come to don't come to class on, or don't come to campus on Tuesday. I'm going to miss them, okay? If they don't walk around wherever I happen to be walking around, I'm also going to miss them. So it's not a random sample. Yeah.
What if you were to change the wording and say that you did this 10 times, 10 different days?
Now, even 10 different days, it's not walking around, no matter how hard I try, is not going to produce a random sample. I either need the list of all students and select them randomly, or I've got to come up with some other creative system to get a truly random sample. And walking around just isn't going to cut it. Okay? Because I'm going to miss people who avoid people who carry on clipboards, right? Because if you walk around campus, sometimes you see someone with a clipboard and you're like, I'm going to take this back, okay? And you're gonna miss those people. So.
Could you give an example of what something random would be in that exact example?
I would just say I selected a sample at random from UCLA. Okay. Now that's kind of a cheat because getting a truly random sample is actually very difficult to do in real life. But we'll just say that if the problem says the sample is obtained randomly, just go with it and say it was obtained randomly. Okay. All right. Does that feel okay? So if I present different situations, different descriptions, you should be able to identify whether any of the conditions, which condition was violated, or if maybe none of them were violated. Okay.
You're not going to trick us, are you?
In my mind, everything's straightforward. Everybody always complains afterwards, right? In my mind, I thought the midterm exam and the quizzes have all been straightforward. But people disagree, so. When I first taught this class, I was like brokenhearted when I got the results of the midterm and final exams. I thought I did something wrong. I thought it was me, but after a few quarters of teaching this, okay, now I'm like 12 quarters in or whatever. I know it's not my fault. It's not my fault. Okay, and I'm not saying it's all your fault either, but I know some people are trying hard, and they just don't get certain concepts. Other students don't try hard. They're not here today, and they're doing poorly. And then others of you are doing great. So the ones who are truly trying hard and you're struggling, okay, like I want to help you. I want to help you, okay. Don't be afraid to ask for help. Don't be afraid to come to office hours or post questions on Facebook. Don't be afraid to ask your friends or use any of the resources I have made available, which are the videos and things like that. So, because at the end, I want you guys to learn statistics and enjoy the subject. And I know that's tough, but I'm rooting for you guys. I really am. Okay. But at the same time, I take my job seriously, and you have to demonstrate understanding in order for me to say you pass. So. Okay. So let's deal with that. Okay. All right. So the last bit is we're going to create something called a confidence interval. Okay? So we learned a little bit about sampling distributions. Now we're going to make something called confidence intervals. Okay? And Eric posed this question earlier, in that he said, how do we know that 40% of Los Angeles is white? Okay? And the truth is we don't. Okay? I've made that number up. Okay? We can go on Wikipedia and we can look at census numbers and we'll get an idea of what percentage of Los Angeles is white. But that's still a guess. Okay? It's a guess based on data that they collected. Okay? It's going to be a pretty darn good guess because they spent a lot of money, but it's not going to be perfect. Okay? Because every day people are born and people die, and the proportions will change ever so slightly, but just a little bit. Okay? Well, when it's a family, when someone is born or someone dies, proportions change a lot because your family is small, right? So if it was just it's your mom and dad, and if it's me and my sister, it's the four of us. At one point, it's 50% male, 50% female. But then, as soon as another child is born, let's say it's a girl, then it suddenly shifts to 40% male and 60% female, right? So it's a huge change when it's just a family. But then, for Los Angeles, people born, people die, so the proportions change just a tiny bit. But because there's so many million people in LA, it changes just ever so slightly. Okay. This is the idea behind a confidence interval, okay? Let's say we didn't know what percentage of Los Angeles was white. Or let's say we take, select a different ethnicity or race, okay? So let's say, let's say we have no idea what percentage of Los Angeles is Latino, okay? Does anyone know approximately what number? Stop. It's probably about, depending where you go, maybe about probably 25 to 30. Something around there, like 20. In terms of, but okay, let's just say 25%. Okay, let's just say 25%. Okay, but I'm making that number up. Let's say we had no idea what that number was. So we take a sample, and somehow we randomly select 200 people. We randomly select 200 people. And out of 200 people, let's say 46 are Latino. Okay, and so what is my p hat here? P hat is equal to 46 over 200, 0.23. Okay, again, we don't know the true percentage in Los Angeles that's Latino, okay? But here I have a sample of 200 people, and 23% of my sample is Latino, okay? So, what can I conclude about the proportion of Los Angeles that's Latino?
What are you asking? One more time?
So this is my sample proportion, right? This is p hat. Can I say anything about p? What is p again? The population proportion. So can I say anything about all of Los Angeles? The proportion of all of Los Angeles that's Latino?
No.
Couldn't it be 0.2?
Okay. So I can't give you an exact answer. I can't say p is exactly 0.23. Okay, I can't say that. But I can say that I'm pretty sure that p is not 90%.
Yeah.
And I can also say I'm pretty sure that p is not 2%. Okay? Yes?
You wouldn't have to do that like a bunch of times?
No. All I have is one sample of 200. It's a random sample of 200. Okay? It's a random sample of 200. And my random sample of 200 is 23% Latino. Okay? So what can I say about all of Los Angeles? Well, what I can say is that P, the proportion that's Latino in Los Angeles, is probably somewhere close to 23%. Maybe it's a little higher, maybe it's a little lower, because we don't know. We don't know if the sample I picked happened to have more Latino people than the rest of Los Angeles, or happened to have fewer Latino people than the rest of Los Angeles. But what I can say is that it's probably something close to 23%. Okay? So I'm going to create what we call a confidence interval. Okay? I'm going to say, I'm just going to make up, I don't want to truly make this up. Just give me a second here. Okay, so let's say I have a margin of error of 6%, okay? And you've probably heard this term. It's equal to 6%. What this means is that I have 0.23 plus or minus 0.06. This is going to be the range of plausible values for P. So I can say I am 95% confident that P is between, and what I'm going to do is I'm going to do 23% minus 0.06. What is that going to give me? It's going to give me 0.17. So I'm going to say I'm 95% confident that P is between 0.17 and 0.23 plus 0.06 gives me what? 0.29. Okay, is between 0.17 and 0.29. Okay, so I can say I'm 95% confident that the proportion in Los Angeles that's Latino is between 17% and 29%. Yes?
Did you get the 95? Are you saying like you're pretty confident, or is that specifically from
Well, I'll talk about this, okay? It just means I'm pretty confident, okay? But I'm not 100% confident. If I wanted to be 100% confident, what would my confidence interval have to be? If I want to be 100% confident about the proportion in Los Angeles that's Latino,
Oh, it would be
Plus
2.09.
0.09.
it has to be, my confidence interval would go from what? 0 to 100%. Okay, if I want to be 100% confident about the proportion in Los Angeles that's Latino, I have to say I'm 100% confident that it's between 0% and 100%. Okay, now that's kind of a useless confidence interval. Okay, I can be 100% confident about anything if I say 0 to 100%. Okay, but here I'm going to say, okay, well, I'm not totally confident. It could actually be something other than something outside of the range, 17% to 29%. But I'm pretty confident that the proportion in Los Angeles that's Latino is between 17 and 29%. Okay? Yes?
I don't know if this is the next step, but how did you get 6%?
Yeah, well, we're going to talk about how I got 6%. Okay, but that's the idea of a margin of error. Okay, is that you put the number that you got from your sample, right? I got 23% in my sample. Right now, that is the best guess that I have for the population proportion. I took, because right now I have no idea what percentage of Los Angeles is Latino. So I took a sample. My p-hat is 23%. That's the best guess I have for p. Okay? And then I come up with some number called the margin of error, which I say is 6%. And with that, I do 23% minus 6%, 23% plus 6%, and I get myself a confidence interval. Okay? So sometimes you see during election season, it'll say, candidate ABC is leading the polls at 53% with a 2% margin of error, right? And so that means they have between 51% and 55% of the vote, which is a pretty good thing if they want to be winning, right? Because if you got over 50%, so 51 to 55%, it seems pretty good that this person's going to win, okay? But if it says candidate ABC has 51% of the vote with a 2% margin of error, then it's not so good, right? Because it goes from 49% to 53%. It's still possible for them to lose with 49%. Yes?
Is this similar to the empirical rule?
There's certain parts that are familiar from the empirical rule, but it's all because of the normal distribution. Yes?
Is the 95% relevant?
The 95% is relevant.
Why 90? Okay.
Yeah, let's, okay. Well, again, the idea is I'm trying to create this confidence interval, okay? I say is from 17% to 29%. What is this a confidence interval for? I'm trying to figure out plausible values of what?
The total population.
The population proportion, P. The P in the population. I want to know the proportion in the population that's Latino. Or I want to know, the proportion in the population that has some trait, okay? Whatever it might be. I don't know that true value of P, so I've taken a sample. And based on the sample, I'm expecting the population proportion P to be somewhat similar to the proportion I got in my sample. Okay? It's not that the population proportion depends on the sample. It's the fact that, the population proportion is some value, but whenever I take a sample, it shouldn't be very different from the population proportion. So whenever I observe a certain value, p hat, I can make kind of an educated guess about where p might be. Okay, does that make sense? Okay. So range of plausible values of p. Okay, so let me talk about how we create this margin of error. Okay, so a confidence interval. For p, for the population proportion p, will look like this. P hat, this is the estimate that I have. Plus or minus the margin of error. margin of error is based on two things. Is equal to what we call a critical value, and the other part is the standard error. Okay. The standard error is very similar to the standard deviation of the sampling distribution. It's pretty much the same thing, except you aren't using the value of p from the population, you're using the value p hat from your sample. Does anyone remember what the standard deviation of the sampling distribution is? Square root of p times 1 minus p over n, okay? This is the standard deviation of the sampling distribution, okay? The standard error is different in that we put hats on the p's, okay? What does it mean to have a hat?
Just from the sample?
It comes from the sample, exactly, okay? So we don't use the p from the population. Why wouldn't we use the p from the population?
We don't know it?
Because we don't know it, right? The whole point of making this confidence interval is that we don't know what p is, okay? We don't know what percentage of Los Angeles is Latino. We don't know the percentage of M&Ms that are blue, or the percentage of cars that are white, and the, I don't know, percentage of people with black hair. Okay? We don't know that. So we have to use a guess, and our best guess right now is p hat, the value that comes from our sample. So this is the standard error. Okay? The critical value, this depends, I'm going to call it z star, and it depends on how confident we want to be. Okay? If I want to be more confident that my confidence interval has managed to actually contain the true value of p, if I want to be more confident about that, should I make my confidence interval wider or smaller?
What?
I should make it wider, right? Just like, let's say if the police are going on a manhunt, right? They say, okay, we saw the suspect flee into this neighborhood. They might create off a blockade, right? They might blockade off certain things. Okay. Now, if they want to be absolutely sure that they caught that they're going to catch the guy, they would blockade the entire neighborhood, right? They would surround the whole thing and have a huge zone where they blockade the things off, right? But if it's too big, it's going to require too much work to search for everyone. Okay. So they can trade off some confidence. Okay. They can say, okay, well, we're going to just search a smaller zone. We're a little bit less confident that the suspect is actually in this zone, but you know, we have a more precise area to work with. Okay, so there's a bit of a trade-off that you got to balance out. If you want to be really confident, you can make a wide confidence interval, and you can be pretty sure that you got the true value p somewhere in there. Okay, but it might be so wide that it's useless, right? Like 0 to 100%. That's so wide it's useless. On the other hand, you can shrink it down. But if you shrink it down, you might actually not have captured the true value of p. Okay? So z depends on how confident you want to be. Okay? Now these values are given in your book, and I'll give them to you now. Okay? Depending on your value of confidence, and the most common values of confidence, so this is the confidence level. Be 99%. These are the most common values that we use for confidence intervals. 95%, 90%, and 80%. Okay? 95% is going to use the value 1.96. 99%, 2.58. Okay? Because we want to be more confident, we make our intervals wider. 90%, 1.645, and 80%, 1.28. These are the confidence intervals that we make. These are values of z star. Okay, actually I should draw a little arrow. that's how you find the margin of error. This is how you make a confidence interval. Yes?
So, the symbol between critical value and standard error, is that a times, is that
Yeah, that's an
plus?
X for times.
Okay, so
times.
you're multiplying that?
You multiply it.
Okay.
Is there a better symbol to use for times?
I've heard you, seen you draw the circle.
Oh, a dot?
Yeah.
Yeah,
I don't-
okay.
That's fine.
Alright. Okay. Yeah, we can do times or dot or no symbol that implies multiplication. Okay.
So once we find the standard error, we multiply it by,
The critical value to get your margin of error, and then you add or subtract your margin of error to your p hat to get your confidence interval. Okay, so let's try this. Let's say you buy a bag of M&Ms. Okay, you want to know what proportion of M&Ms are blue. Don't you know? Or don't you want to know? I don't know.
You never get blue.
Does anyone remember when blue was adopted as a color?
Yeah.
Yeah.
Mhm.
No, I'm not. It happened in my lifetime. Okay. What happened? What else happened in 1906? Anyone know? Your grandpa was born? Good. All right. What proportion of M&Ms are blue? Okay. We buy a bag full of random M&Ms. How many M&Ms come in a bag?
we'll say 30.
Let's say a big bag.
Oh,
50.
100.
200.
Costco
Alright.
size?
10,000.
So let's say a large bag
500.
with okay, 550 M&Ms. Don't eat them all in one sitting. Okay. Are these peanut? No. Okay. 550 M&Ms, and let's say let's say 103 M&Ms are blue. Okay. Let's say 103 M&Ms are blue. Okay. Make a 95% confidence interval for the proportion that are blue from the factory. Okay. just one more decimal, but that's, yeah. I would say keep 3 decimals at least. You guys can try it. You got any of the numbers right?
Yeah.
You got the 0.1873, correct?
Yeah.
Eric?
I think it's a 0.1547.
1873 minus 0.0326. Okay, we'll go through this. Okay? Alright, so our margin, our confidence interval is going to be p hat plus or minus our margin of error. What's our margin of error? It's our critical value z star times the standard error, which is the square root of p hat times 1 minus p hat over n. Okay, what's p hat? P hat is 103 divided by 550, 0.1873, yeah?
Yeah.
Something like that. Okay. What is my z star going to be?
1.9.
Okay. 95% confidence, I'm going to use 1.96. And what's my standard error? Standard error is going to be 0.1873 times 1 minus 0.1873 divided by 550. Okay, and that comes out to be something else.
Why is it?
It's not p hat over n.
Oh wait.
It's p hat times 1 minus p hat over
I
n.
wrote it
Okay?
down wrong. No wonder.
Okay?
Damn.
103 is how many M&Ms that are blue?
Yeah, which is
That's not p hat. No. What is p hat? P hats are sample proportion.
No, I know, but I'm saying what's the number in this one?
So p hat is 103 divided by 550. So that's 0.1873. Okay. P hat can't be 103. Okay? Because p hat is a proportion. It always has to be between 0 and 1. Okay? So I can't get a number like 103. It always has to be a decimal. Okay? Always has to be decimal. Okay, so my standard error, I get 0.0166. Okay, I left a few more decimals in my calculator. Okay, so when I do that, I have 0.1873 plus or minus 1.96 times 0.0166. Okay, and when I do that, I get 0.0326. That's what I'm getting here. So I have 0.1873 plus or minus my margin of error, which is 0.0326. So this thing is my margin of error.
Quick question. From the standard of error,
Yeah.
then is the next step going over to where the 0.873 plus minus?
So I'm
I'm
plugging
trying to
in.
follow the steps.
I'm sorry?
I'm just trying to follow the steps, so.
So I found, okay, so I started off with this, right? Because this, I know my confidence interval looks like this. So I'm just plugging in my value for p hat,
Correct.
or 1873. I'm plugging in my value for z star,
Okay.
1.96.
Okay.
Okay? And I'm plugging in my value for this entire thing, which I calculated separately, the standard error, which is 0.0166.
Okay.
Okay? And I did that, and I got 0.0326.
But you first had to do this standard.
Yeah,
error.
yeah, we had to find the standard error.
Right.
Okay?
Oh, you multiplied it again.
So once I found that, I got this,
You multiplied it by
and then I did 0.1873 plus this value,
Okay.
and I got this. and then I did 0.1873 minus this value, and I got this. Okay, so this is my confidence interval. My 95% confidence interval. Rugia.
Yes, we have the,
I know.
will you give us like, say, okay, your confidence level is 95, or if like, say, I say, oh, my confidence level is 95, this is 99%.
Yeah, I'll give you the confidence level. Okay, I'll say make me a 95% confidence interval. Make me a 90% confidence interval. Okay, something like that. All right, what do I say? What is my interpretation of this confidence interval? So I'd say, so what can I say about this? I am 95% confident. All right, you guys, just you're gonna see something like this next week, okay, on the quiz. So pay attention. I am 95% confident. What? Confident that.
P is the amount of blue.
Yeah, the proportion of blue M&Ms. What about the proportion of blue M&Ms?
Between
Is between
0.15.
0.1547 and 0.2199. Okay? I'm 95% confident that it's between those two values. Yeah.
Okay, I get it.
I just did 0.0166 times my z star. What's my z star? Okay, so punch in your calculator, 0.0166 times 1.96. And you should get 0.0326. Okay. All right. Is this good?
Yeah.
Okay. So in your homework, you'll have a few exercises to make confidence intervals. You will see a confidence interval also on your quiz next week. Okay? You're going to see a confidence interval on your quiz next week, and you'll also see confidence intervals in your homework. So get your practice down. Make sure you can do a confidence interval based.
Do we need to memorize the c-values for the confidence level?
You should write. You get a note card, right? You should put those somewhere on your note card. Okay? Put your z values somewhere on your note card.
Confidence level. Okay.